Okay, so Rolle's theorem, we played around with it a little bit. We had two y values that were the same with different x's. And if you try to connect those with a continuous, if it's continuous between those 2 points and differentiable, that means that it has to be smooth connection between them. One way is to draw a horizontal like that. Another way is we could come up and back down, or just go up once maybe. Like you could also do this or go down. Any of those scenarios, right? All of those, as long as it's continuous and differentiable, which is what Rolle's theorem requires, that f is continuous on the closed interval and differentiable on the open interval between 2 points. If the y values, so f of a and f of b, are equal, then there's at least one point where this or number c from a to b for which f prime of c is equal to 0. So in other words, there's at least one horizontal tangent line. Case number 1 is here. So I'm letting f of a equal some letter d, some constant d, where f, which is equal to f of b. So those are the y value at the endpoints. If the whole function is equal to that constant, so in other words, it's a constant function. That was the first one I drew, the red line there. For all x in a to b, then f of x is constant on that interval, which means we've shown the theorem for that, which means f prime of x is equal to 0 for all the x's. So Rolle's theorem holds true in case number 1. Case number 2 looks like this. Consider f of x greater than d. So in other words, the function is above some value d. So it goes up, or the endpoint. So like the f of x in between the two endpoints are going to be above that letter, that y value. So for some x's, by extreme value theorem, we know f of x must have a maximum value at some point c on the interval, because we know it's given that it's continuous and it's also closed. So by the extreme value theorem, we know that there's going to be some maximum there. Now, the one thing we know, if you think about it, since f of c is greater than d, so you've been told on the interval from a to b, not including the endpoints, f of x is going to go upwards. It's going to be above that value, those y values. So the maximum can't occur at the endpoint because there is some value above the endpoint y values, so that letter d. So that means then that f of x has a maximum on the open interval from a to b. And if that's the case, it follows that f of c is a relative maximum. So the absolute max is also the relative maximum. My theorem, it's not my theorem. There is a theorem. We know that's supposed to be a by theorem, like it doesn't have a name, but there was a theorem. We know that relative maxes and mins can only occur at critical numbers. Remember, critical numbers happens when the first derivative is either equal to 0 or undefined, right? So those are the two options. Either f prime of x is equal to 0 or f prime of x is undefined. That's where the critical numbers happen. However, because this is differentiable everywhere, it's given that f of x is differentiable at x is equal to c. It's given that, by the way, it's differentiable everywhere. That means f prime of c has to equal 0 because you're being told that it's differentiable everywhere. It's not undefined anywhere. So that's how we know that f prime of c has to equal 0 at some point on that interval. And that is showing for the case that, the function is above the y value somewhere. Well, it's the case number 3 is that if you happen to be below, consider f of x is less than, is less than d here, like that, for some x values. The proof is exactly the same. The only thing, instead of a maximum everywhere, like it's by the mean value theorem, then we have a maximum that can't, and the maximums can't occur at the endpoints. And you know that there has to be at least one relative maximum, which is also going to be the global or the absolute maximum or minimum, excuse me. So that's it's the same proof. So case 2 and case 3 are the same, except anywhere you see the word maximum, it's going to be replaced by a minimum.